before I left.
You ready to get started?
Pardon?
You ready to get started?
Yeah, I'm ready anytime you want. Does anybody have a long stick? My finger doesn't reach that long.
Jason, do you have your pointer with you anything?
Ready?
Well,
I do have a role to play in this.
Okay, we'll go ahead and get started. I'd like to introduce Dr. Ravi Venkatesan. He's from the Systems Research Corporation in Pune, India, and received his PhD from the University of Illinois, Urbana. And he's here today to talk about knowledge discovery through the Fisher information game. This work was sponsored, I guess, principally by the Microsoft Research Corporation. Thank you.
well, first of all, I'd like to thank every one of you for coming here. And I'd like to thank Professor Robert Fry for inviting me here. And I'd like to thank my sponsors for paying for this research. And last but not least, I'd like to thank a common friend of Professor Fry's and myself, Professor Roy Frieden, for teaching me this theory. So let's go into action. Now, what we're going to do here is we're going to try in 1 hour to introduce both the Old Testament and the New Testament. That is theory and application, because we are using a scheme based on a Fisher game to reconstruct probability density functions from observational data. And as a consequence, knowledge discovery. We're going to introduce the quantum mechanical aspects of this process. Now, first of all, we all heard about invariances in computer vision and pattern recognition, and we heard about invariances in statistical learning. We've heard of invariances in computer and graphics design, computer-aided graphics design. But the issue is, what do you mean by an invariance? An invariance is invariance of under the action of a group, like rotation, translation, angular momentum, Galilean invariance, Lorentzian invariance, scaling invariance, that is self-similarity, etc. Now, the issue is that in statistical learning, most of the problems of, and in CVPR and CAGD, most of the problems involve discrete data. So, the traditional textbooks of invariance, inverse symmetry invariances, was written by Peter Olver and at University of Minnesota, and they involve continuum models. Now, that might not work in statistical learning, because in statistical learning problems, most the problems are inherently discrete, and if a continuum does exist, is going to be prohibitively restrictive in nature. So how do we go about solving the invariances? Because why do we need the invariances here is that we are modeling the Fisher game as the variational extremization of a variational principle or a Lagrangian. And so you need the basic tools to solve this problem for discrete data, intrinsically discrete data, without resolving to a continuum. So we went back to the theory of Tsung-Dao Lee. Tsung-Dao Lee got the Nobel Prize in Physics, along with Chen-Ying Yang, for disproving the law of parity and stating that parity has a twist and space has a twist to it. Now, what Tsung-Dao Lee in his seminal paper in the Journal of Statistical Physics did was turn 3 centuries of misconception, preconception, or bad conception on its head. And where he said that was our prior conception that the discrete is an approximation to the continuum is wrong. Actually, the continuum is an approximation or subset of the discrete. And he proved that. Now, this paper here has been, this work here is part of from a paper which is being published at the Foundations of Data Mining section at the International Conference on Data Mining. Frankly, I don't know how a paper like this ever got into there, But anyway, I'm very happy about that. Now the shortcomings in present invariance preserving models to treat observational data. Now observational data, what do I mean by observational data? I measure you, and then you give a response. And then I measure Professor Fry, he gives a response. I measure the other professor, he gives a response. I measure you. You're all disparate data. Now I cannot form a continuum from you because I do not know what model you represent. Now the hallmark of T.D. Lee's theory is that you can calculate a variational calculus based by mapping Poincaré's lemma onto discrete spaces. So as a result of which you go from Professor Fry to him to you and to you using shift maps. Now the space between the two of you and the two of you and the two of you is non-differentiable. Now this may have a fleeting and passing similarity to finite difference approximations, but these are governed by the discrete variational complex is governed by rigid axioms coming from Poincaré's lemma, and these are not ad hoc methods like finite difference approximations. Now, what's the utility of measurement response models? These days, it's normally thought it's better to get the system of phenomena under study to tell its story than us coming up with a model and trying to fit it onto the phenomena. So many times, as you all know, trying to figure out a model and then fit it onto a phenomena is like fitting a size 10 foot into a size 9 shoe. It may not work. It doesn't work most of the times. So this is basically a classical inverse problem where you can use a minimalist approach by putting in the minimal amount and like putting a straw into a liquid and figuring out the contents of that liquid. But as long as if the theory is sound, I mean, it's okay. Otherwise the minimalism starts creeping in and distorting facts. So we are trying to make the theory, try to make the theory as sound as possible. Now, what's the significance of Fisher information as a measure of disorder or uncertainty? Well, there are three significances of Fisher information. First of all, Fisher information is a local measure of uncertainty. Can I use the word uncertainty here? And then afterwards we can use the other word. And
uncertainty is good, but you're going to define local.
Pardon?
Uncertainty is fine, but we don't know what local means yet.
Local means it has a derivative term, so it changes from position to position and time to time. You
local and time. Okay.
Yeah, and position. You can evaluate a spatio-temporal change over microscopic distances. Now, the next advantage of Fisher information is that on variational extremization of a Lagrangian, that is a cost function that contains Fisher information as a measure of disorder, you get a system of equations which resembles the Schrodinger equation in quantum mechanics. Now this is very important because it gives a quantum mechanical representation to statistical processes. Now one of the main reasons why this work was done was in an attempt to get a quantum register going on to measuring qubits or quantum bits. And the third, it's very useful to have a tool that swings from quantum mechanical phenomena to statistical phenomena and back and forth. I'll explain as we go ahead what we're doing. Then the third significance of Fisher information is that because of the derivative term, it maps an optimization problem into differential equations. Now you are all natural language processing, some of you are natural language processing people. I'm sure you've heard of two works in NLP. One is by the feature extraction work by Della Pietra, where he uses a Markov model using Maxent, and then uses the iterative scaling approach. And then you also heard of an equivalent work done by Naftali Tishby. I believe Tali was here doing his on sabbatical for a year, and Tali and Amir Globason had come out with a concept called sufficient dimensionality reduction. Now there they use projection onto different spaces. Now basically you can look at Tali's work as a subset of this particular model. And in fact, one of the relationships in a sufficient dimensionality reduction, Tali has talked about in his paper in JMLR, Journal of Machine Learning Research. Tali has talked about a particular relationship which is valid for sufficient statistics. That relationship is essentially the Kramer-Rao bound. So I just wanted to draw attention to some of the issues in which you are familiar with. Now, what are the objectives of this particular talk? Now, the first is to demonstrate the equivalence between a statistical process and quantum mechanics. I've explained that part. Now, data reconstruction as a Fisher game. Now, there's a plethora of methods to reconstruct data. I mean, there's neural networks, there's Bayesian models, there is regularization theory. So the issue is, what's so special about this approach that made us take it? And this approach brings in a quantum mechanical aspect to the data reconstruction, which is absent from other approaches. Then finally, we talk about Fisher, we test the efficacy of Fisher information as a contrast function in independent component analysis. And we show where independent component analysis comes in here, and then afterwards we show where Fisher information is so important. Now, what is EPI basically? Now, EPI owes a lot to the Szilard-Brillouin theory of measurements. Now, suppose you have two conjugate spaces here. You have position, and you have momentum, to give an example. Now, you have an observer that makes a measurement on a physical phenomena, and which has got what is known as the source effect. The source effect contains all the known properties and constraints of the system. Now, owing to the perturbation of the phenomena releases a portion of what it truly contains out in the form of bound information. This term bound information came from the Szilard-Brillouin theory of measurements, and in Brillouin's work it referred to the thermodynamic properties of the system, but in extreme physical information the bound information could transcend thermodynamic properties, and basically it is the Fisher information in the conjugate system space. Now you can treat conjugates in this case as one would treat the Lagrange multipliers in Naftali Tishby's work on SDR, where he has talked about conjugate Lagrange multipliers. Well, that's very similar to this, but this has a broader sense. So just to keep those of you awake who are aware of Tishby's work, but might be bogged down with this particular aspect. And then this bound information goes through here through a unitary transformation. A unitary transformation is nothing but a translator to translate state functions like probability density functions and coordinates from one conjugate space into another. And then it goes and perturbs the observer. And then you can find out the law and the unknown law and the probability density of this by measuring it, the response of the system here. Now, are we clear with this? Any questions? Yes, there is a question. Where does the game come into the picture? Okay, I'll tell you where the game comes into the picture. Now, the observer would like to maximize the Fisher information available to her or him. But the physical phenomena is like the Maxwell demon. It wouldn't like to tell much about itself. So there's a game going on between the observer and the physical phenomena. And we model our system so as to have minimum Fisher information here that corresponds to maximum uncertainty at the observer's end, which will lead to the observer learning, a flow, a gradient in the learning process would be guaranteed, I would say, at the observer's end. Because you can look at it as water flowing into a trough. If you have uncertainty, then water is going to fill in. But because the uncertainty corresponds to the emptiness in the trough. But if the trough is full and you don't have uncertainty, then it's going to. Would that be a good analog? Tolerable?
Excuse me. What do you mean by maximizing the Fisher information matrix? Is the matrix value quantity? How do you maximize that?
I'm just getting to that.
Okay.
Now the observer makes two types of measurements. Now the observer has independent measurements made on this system. Now there are two types. Type A is she or he can make n different measurements on a single particle or a single datum or a single macro particle. That would lead to equiprobability in the quantum mechanical sense of a particular particle or a particular macro particle being observed. So that is equivalent to a person trying to sample a liquid using a straw, which the liquid's in a trough. This is the system space. This is the observer space. Now, what's the measurement part of this? He creates a suction to bring up the liquid, and then afterwards, that's the measurement. The response is going up. The liquid travels through the straw. So the straw is a channel capacity in this particular case. Now this is one way to look at it. Another way of looking at it is that the observer keeps on changing its position through arbitrary but small distances and samples it from different straws. So you make either n different suctions through one straw, or you have n different positions from where the observer can make his measurement or her measurement. And this particular type of measurement scenario could lead to ergodicity or mixing. We'll discuss that issue later on. Now, this is what is measured by the observer. This is the I would say the crude measurement made by the observer. This is the parameter that needs to be calculated, and this is the residue, which is a noise or random noise. So this is known as Mach's principle in Fisher information. Now this is the amplitude, which is the square root of the probability density function, and this is the perturbation of the amplitude. Now you ask a question, where does the minimization of the matrix comes in? When we talk about independent measurements, we talk about independent data, and therefore we have the Fisher channel capacity, which is a trace of the Fisher information measure. So this is type A, where you have 4 into n, because n is equal probability, and this is type B, where you have n equal to 1 to n, depending upon the amount of places where you can have it sampled. So now I guess I answered that particular question of yours. Now in the system space, you have, the system is conjugate to the measurement space, you have an amplitude, and then you have the unitary transformations here and here. So you say that the Fisher information in the measurement space is equal to the bound information in the measurement space, and the variation of the Fisher information in the measurement space is equal to the variation in the bound information in the measurement space. But the bound information is essentially the Fisher information in the system space, or the space here. So it has to be subjected to a unitary transformation in order to be measured here. So this is the particular unitary transformation, and this is a unitary operator. It operates and gives us this. This operates and this operates on the amplitude and gives us this, and the basis function coordinates follow this particular relation. Now select applications of EPI. Quantum mechanics, statistical physics, fuzzy clustering. It was done by yours truly and another person in France at the CNRS, named Michel Menard. Then it has been applied to carcinogenesis, econophysics, image denoising, myself and a colleague of mine in Holland, signal processing, time-independent data reconstruction, this seminar, then time-dependent data reconstruction and clustering, which will be published in PRL in 2005, and dimensionality reduction and time series prediction, which is done by me and Professor Jose Principe, who is the director of the CNEL at the University of Florida. Now there's an analogy between EPI and the Szilard-Brillouin theory, where Brillouin used what is known as the Szilard engine, and an explanation of the Szilard engine can be, a good explanation is in the book on complexity theory by Paul Vitani and Ming Li. Now we know from the book on robust statistics that Huber changed the Maxent Lagrangian by removing by replacing the Shannon information with the Fisher information. Now these are Lagrange multipliers, and these are constraint terms which are connected with the data. So the similarity between MFI and Maxent is that minimum Fisher information merely replaces the Shannon information with the Fisher information. Now in extreme physical information, which was propounded by Frieden and Sofa, it's a zero-sum game between the gedanken observer and the system or phenomenon, which is nature, which we had explained prior to this. It is based on the I theorem, which means that, which says that as time progresses, the Fisher information reaches its equilibrium value. This implies that the Fisher information is a monotonic description of or representation of uncertainty. Now both MFI and EPI yield maximum entropy-like solutions for equilibrium distributions. Now the importance of unitary transformations is that it acts as a translator from the phenomena space to this space, the measurement space, and the existence of a unitary transformation guarantees an extreme physical information solution. A third aspect is that the existence of a unitary transformation between the space of the measurer and the space of the phenomena is that it carries a quantum mechanical representation with it. Now, what's the rationale for an invariance preserving criteria for extreme physical information? Now, the present theory of extreme physical information uses invariance and conservation properties in a somewhat heuristic manner. It's not wrong, but it's heuristic. So what we try to do is apply it to put it on a more fundamental footing and to give it an application to make it practically applicable in problems like data reconstruction. Now, discrete invariances. Continuum models are a subset of discrete models, Sundal-Lee. Now, these are some of the references on discrete invariances, and it extends continuous variational complex to discrete spaces by projection of Poincaré's lemma onto discrete spaces. It accommodates continuum-free lattices and simplexes, and it allows for derivation of Noether's theorem and conservation laws. What is Noether's theorem is, for every symmetry that is admitted by a given Lagrangian, which is known as a variational symmetry, there is a conservation law of the form del dot phi equal to 0. And that is what Noether's theorem gives, and this allows for that in discrete cases. Now, the extreme physical information in axioms are the variational derivative or the Fisher channel capacity minus the bound information, and that should be equal to 0. And this, the Fisher channel capacity minus kappa into the bound information equal to 0. What happens with, what is kappa? Now, suppose we don't have a unitary transformation, then kappa is an efficiency function between 0 and 1. But if there's a unitary transformation, I equal to j. Now we have the well-known minimum Fisher information. So what we state is, in order to systematize it, that the data terms in the minimum Fisher information theory is the bound information in EPI. So we are not only trying to draw an analogy between MFI and EPI, indirectly we are drawing an analogy between Maxent and EPI too in certain cases, because these, however, the Maxent Lagrange multipliers will be different. So we are trying to mate them together. So the MFI data constraint terms manifest the EPI bound information. Now, as a density estimator, we use Chebyshev-Hermite expansions for density estimation. Why is that so? I'll tell you why. We want to have a quantum mechanical representation for a statistical problem. Now, even if you take a perfectly Gaussian data and you reconstruct it, you're going to find noise. And the noise is pretty bad. And where does that noise come from? It's called reconstruction noise, and it lies in a space which is orthogonal to the reconstructed vector. So what happens is that at each observable, at each point which we observe, we emulate a quantum mechanical harmonic oscillator. Why do we do this? The answer is very simple. The quantum harmonic oscillator is a fundamental quantity in quantum mechanics. Now, it contains many energy levels. The zeroth order energy level corresponds to the Gaussian distribution, and higher order energy levels corresponds to deviations from Gaussianity. So in this way, we can relate the effects of the high frequency noise from reconstruction to the energy levels of the quantum mechanical harmonic oscillator. So the effects of reconstruction noise can be related to the QMHO. The correspondence between high frequency terms in the CH expansion and the QMHO energy levels. Now the CH expansion, or the Chebyshev-Hermite expansion, is also known as the Hermite-Gauss expansion. It has another advantage. It is the fundamental solution of the information theoretic transport equation, or the Boltzmann's equation. So it is a fundamental solution for that particular problem. So it serves two purposes here. In this case, means each deviation of Gaussianity from Gaussianity will emulate an energy level at a given observable. Now, using T.D. Lee's approach, we calculate the invariant cost functions, and then we take the lattice variational and zero conditions by using discrete variational calculus, and this is the shift operator, and we get this as the Euler-Lagrange equation and this as a zero condition, and these two had to be satisfied simultaneously at each lattice point or vertex on a simplex. Now the data point which is observed is the expectation of the observable. Now the distinction between the present approach and prior attempts to model QM in the inverse problem of statistics. This is known as a quintessential inverse problem of statistics, and I'll tell you why. What's the difference between this approach and prior approaches? In prior approaches, in using quantum mechanics, we assumed that we knew this particular term. Why? Because what they did was, in reconstructing data, they reconstructed known potentials whose analytical solutions they knew, whose analytical forms they knew. In this case, we don't know the form that we are measuring. So we just can't come up with any ad hoc assumptions. Now the discrete observables are represented as the index of the observable and the space between the present observable and the next. Now, using the well-known theory of canonical quantization between these two, between the coordinate, Cartesian coordinate, and the momentum, we introduce it in the form of the discrete variational complex of T.D. Lee. Now I'd like to draw an attention to one particular fact. We had said that this work was initially started to measure quantum registers. In this particular case, we're talking about measurements here. In quantum registers, we measure, that's in quantum information theory, we measure, we make measurements, simultaneous measurements within the Heisenberg uncertainty principle, because you can't make simultaneous measurements, but within the framework of the Heisenberg uncertainty principle, we make measurements in both conjugate spaces. So that's the difference between this problem and the problem of quantum registers. Both are important problems. In one is in quantum computing, and this is in exploratory data analysis. Now, from taking the variational minimization, we arrive at the time-independent Schrodinger equation. The time-independent Schrodinger equation is basically a Riccati equation, a form of Riccati equation, and it's and the most prominent symmetry is the scaling symmetry. However, if you go back here, this particular expression, when you go through the algebra for that particular case, does not contain the scaling transformation. So what you do is you do what is known as you carry out what is known as homotopy, or the inverse problem in the calculus of variations, and we find out an effective form of the Fisher channel capacity, which is this. Now you may notice that this resembles the Fisher channel capacity, the usual Fisher channel capacity here. Subjected to a single integration by parts and followed by a normalization. So we call that the effective Fisher information. So now we are all in order with respect to this, and then we get the form of the time-independent Schrodinger equation, which is a tridiagonal system of equations in this particular form. We do not know these, and we have to calculate these. So this is an ill-posed problem, and we try to get as many representations as possible of the Fisher channel capacity. So multiplying throughout these respectively by the amplitude, which is the square root of the probability, we get another definition of the Fisher channel capacity to be this. Now the question is, how do we relate the number of higher order harmonics, that is high frequency noise, to the excited states of a quantum mechanical harmonic oscillator? Well, the answer is very simple. We have the quantum mechanical virial theorem, which states that the expectation or the potential energy is equal to the expectation of the kinetic energy. In this particular case, what is the kinetic energy? It's the Fisher information. And what is the potential energy? It's the bound information. So, from the quantum mechanical virial theorem, using discrete calculus, we arrive at this, and then we arrive at a relationship between the Lagrange multipliers, the distance between the observational data, that means my measurement of you transferred into my space, and the states of the quantum mechanical harmonic oscillator. So this is the first semblance of linking a statistical process to a quantum mechanical process. Now, we all know about the Legendre transform structure, which links by reciprocity and duality the information theoretic criteria with Lagrange multipliers. So expression, we derived a form for the LTS, or Legendre transform structure, for the Fisher information matrix for lattices. Now in lattices, the orthonormality condition is this. You may ask yourself this question, why this delta n? Well, that's because we are operating in lattice space. If you take normally if you take the orthonormality condition, where does the term orthonormality come from? Orthogonality and normality. In the continuous form, you have only the chronicle delta, but here we have to have a division by their space. And if you take the continuum of this, you'll get the derivative of the PDF, and you won't get the PDF itself. So that's one point to remember, and it's well written in a book in quantum mechanics by Kittel. So this is the orthonormality condition for lattices. Now the inverse problem in statistics. Now our job is to minimize the Fisher information at the observer's end. So we introduce this particular form of ansatz, where this is the basis function and these are the eigenvectors. Now this is a mixture basically of, you can look at this approach, now that we are talking about eigenvalues and eigenvectors, this has a similarity to the work of Silva, but who has solved the problem of bound states using eigenvalues and eigenvectors, but within the Bayesian formulation. And he has not talked about a game. And he has, in our particular case, we are using a similar approach, and this is the normalization condition. Now, these particular coefficients here correspond to high frequency data, high frequency noise. Now, using this particular representation, we can come up with a form of the Fisher information matrix based purely on coefficients, using the orthonormality condition. In this particular case, we have shown it for channel capacity, but you can fill in the others too for non-IID data, as you've done in your paper in Appendix A. And in the asymptotic limit, we have the variance from the Kramer-Rao bound. Now, from the expression for the harmonic oscillator here, we arrive at a form of the Fisher information, which is this. Now, each of these can be equated to get a deeper relationship between the statistical process and a quantum mechanical process. And the high frequency terms, or the terms that correspond to the reconstruction noise, surprisingly turn out to be multiples of the ground state basis function. That means C1 is equal to 1/2 C0, C2 is equal to 3/2 C0, C3 is equal to 5/2 C0, etc., etc. So all we have to do now is to figure out what is the basis function coefficient, and this form of Fisher information is dimensionless, incidentally. It's all in the form of coefficients. And we get this to be the form of the ground state coefficients, and this is all contingent to the normalization condition being solved. So the question is, how many terms do we need? You may ask yourself, how many excited quantum harmonic oscillator levels would you need? You keep calculating C1, C2, C3, etc. till this is exactly or nearly exactly satisfied. And that's the number you need for a proper reconstruction of data. Now the question is, are we really consistent with the inverse Schrodinger equation? Now there is a classic textbook on this by Zakhariev and Susko at the Moscow State University, and it's printed by Springer Verlag, and it's referred to in my paper. And we adapt the derivation over there and express the orthonormality condition in forms of energy, and then we arrive at a set of recurrence relations which have to be satisfied in order to establish the fact that the inverse Schrodinger problem is actually being solved in this particular case. Why inverse Schrodinger problem? Where did I get the term inverse Schrodinger problem and not forward Schrodinger problem? The reason is we don't know the values of the Lagrange multipliers and the potential. So these have to be solved. That's why it's an inverse problem here. Now there is one very important observation that we figured out, and that is that this particular form of ansatz always, regardless of the number of terms involved, leads to minimizing of the Fisher information at the observer's level. Now this is a very important result from the viewpoint of practical applications. Now we highlight the implementation of this from the paper. I did a copy and paste from my paper. So this is the algorithm. We have the known parameters, which is IID optimal data generated from a MATLAB random sequence generator, which corresponds to a mixture model. You have the unknown parameters, which is the spacing between the observables, the Lagrange multipliers, the energy multiplier, and the probability density function. We can take the distance between two observables to be the distance between two observational data, since it's arbitrary. However, we cannot take the positions of the observables to be the positions of the observational data, because the observational data are the expectations of the observables. So they cannot coincide, but they can be equispaced if they can have the same spacing from each other. Then we evaluate the coefficients, and we evaluate the higher order coefficients, and you using from the so that it satisfies the normalization. Then we need to initialize the problem. So to initialize the problem, we calculate the Lagrange multipliers from this particular relationship. But we found that numerically evaluating it, this particular relationship after a few steps tends to diverge. So we get a few first initial values from this relationship that links the statistical parameters to the quantum mechanical parameters, and then use the Legendre transform structure after that to calculate the other values. So evaluate the Lagrange multipliers at each discrete observable using the quantum harmonic oscillator relationship for initialization purposes. This may be used. And 9 is the Legendre transform structure. For initialization purposes, a QMHO relationship may be used. And then we saw the recurrence relationships for the time-independent Schrodinger equation. And then afterwards, we want to make a check that everything is okay. So we utilize at the end of each iteration epoch, we utilize the steepest descent approach and make connections to the values of the Lagrange multipliers. So we are absolutely sure that we are on the right track. Now we have a mixture model of these particular characteristics. The solid line is the exact Monte Carlo simulation, and these are the reconstructed data, the dotted lines, and this is considered to be a decent reconstruction, to say the least. Now the question is, how does this particular form of ansatz figure out, a person is going to ask, say, for example, my program manager asked me this question, how does it refer from other ansatz? Because he had his mind fixed in Parson windows. You have some first-class density estimators like Parson windows, histograms, etc. Now, there are 2 points that need to be noted. First, these eigenvectors can also be calculated from histograms or other density estimators. And second is, without using that, we use our theory. Here, this is a true distribution, the diamonds. This is our theory. The red is Tensov estimators, which is among which comes your Edgeworth and Graham-Charlier or any other orthogonal series. And then you have your green, you have your blue, which is your Parson windows. And you can see that the Fisher game hugs the contours most closely. It is superior in performance to Parson windows. And anything is better than Tensov estimators in this case. Now what happens if you reconstruct data? I told you that you're going to get high frequency noise. What happens if you reconstruct data from reconstruct observational data without adding high frequency noise? So this is what you're going to get. These are the effects of high frequency noise. So this comes under the heading, don't let this happen to you. It looks horrible. Actually, it's supposed to be Gaussian. Then we establish along the lines of Tikhonov and Arsenin a form for calculating the optimal number of harmonics and the residual between the reconstructed probability density function and the actual but unknown probability density function, and we find out that the effects of smoothing, actually there's a point here which did not come. You have just one basis function is going to be pretty bad, but afterwards the more the number of basis functions you have till you reach till you satisfy the normalization condition, and afterwards saturation takes place. Now, why does this happen? Because the energy term here this energy term provides a regularizing effect. And what are we comparing this with? The usual methods of reconstruction using maximum likelihood estimation. And you have a decrease in number of basis coefficients up to 50%. Now we talk about the effects of correlation and ICA for 5 minutes. Now I'll tell you what, where does correlation come into the picture? Now in our synthetic experiment, we used a random number generator, a random sequence generator, which was IID. Now, just because our measurements were done independently, it doesn't mean that the system is going to give us uncorrelated data. They're going to be correlations. And what do we do with those correlations? So this is the process we're going to follow. First of all, I'm going to show you a twofold approach. First of all, the procedure and how to deal with this kind of problem. And the next is how does Fisher information in general behave as a contrast function in ICA. So we obtained observational data from the Fisher game with correlations. You set, instead of AXN equal to 0, AYN equal to 0, AYN is equal to DN. So you have a mean. You do a PCA, a principal component analysis, and then afterwards you get the full Fisher information matrix, which you discussed in your paper, but which we can express in the form of coefficients. Now from PCA, you're going to get Whiten data, you're going to get uncorrelated data, but even Mickey Mouse will tell you that uncorrelated data does not equate to statistically independent data. So you have to parameterize it using a Givens rotation, which is a unitary transform, thankfully, and then you obtain IID data. In this case, the measurement response scenario, where here is the theta or the parameters are the Givens angles of the diagonal elements. Then you play the Fisher, then you plug in the ansatz, you perform the Fisher game, you get the reconstruction, and then you do an inverse PCA to get the reconstruction with the correlations included. So that's the true answer. So this is the outline of the ICA process. Now what happens? We take in a traditional ICA situation, we wanted to see how Fisher information and the Fisher game works. You have input data, which is unknown. You have a mixing matrix, you have a whitening matrix, you have the output, you have the Givens-Jordan rotation, and then you have you have the observables, and then here you have the output. Solution strategy, we assume the measurements are made with zero mean. You do a PCA. This is a diagonal eigenvector, eigenvalue matrix, and this is the orthogonal eigenvector matrix. Then you have the Whiten data, you parameterize by Gibbons permutation, and then you parameterize the Fisher information Lagrangian with respect to the Gibbons angle. You update the Gibbons angle by this particular relationship, which saves us the necessity of using stochastic or natural gradient to update the Gibbons angle. And then we calculate the signal to noise ratio in this particular form. We can calculate the signal to noise ratio at the output channel because we know the value of the whitening matrix. And this is what we get. This is the signal to noise ratio, number of constraints, number of data points. It increases with the more the number of data, or more the number of data point, more the number of data, the more the number of constraint terms you require, and hence more the number of coefficients, which is okay. And now this is an interesting graph because here we use a 2 by 2 mixing matrix of Gaussians. Now in this particular case we use a 3 by 3. You use one sub-Gaussian, one Gaussian and one super Gaussian, which is a Laplacian in this particular case. And then you have, we compare the ICA results for the Fisher game, to Maxent, to Comon's minimum mutual information, to the fast ICA, which is one of the most prominent ICA packages around, and Infomax. Now why is Infomax down here? The reason is very simple, because Infomax has got the sigmoidal nonlinearity, and which sharply differs from the form or the cumulative distribution functions which are involved here. And you find out here that the Fisher game separates far more efficiently than any one of these. Now, summary and ongoing work. Max Welling and myself are using the beta energy, which is defined in this particular form. Now, beta energy is normally looked at in the graphical, in belief propagation, in terms of phase transitions. In Fisher information here, we are not using phase transitions, although Don Johnson has used phase transitions, has related Fisher information to phase transitions in exhaustive series of work. But what we are trying to find out is an optimal minimum it can be reached, which is in deterministic annealing equivalent problems within the framework of a Fisher game, so that you can reach an optimal minimum. Now, we are using this with applications to web data mining and image texture analysis. Now, I leave us all with one question to ponder out with is, do measurement response models transform unsupervised learning to reinforcement-like learning? It means you have an observer participation, you have a cost-to-go function, and so do we have a reinforcement learning type of problem. Thank you very much for your time.
Still, Frieden and you both refer to Fisher information as a measure of disorder. And I've talked to him about this too, but in terms of thinking about this as the game paradigm, the nature is trying to maximize disorder, minimize order. And the way it's cast, minimization is over nature's component. So it seems like even that side, it's really sort of reversed. It's really more of a measure of more of a positive technical measure of order, or a measure of distinguishability. It's kind of a subtle point, but it seems like that still is the case. Whereas entropy is a measure of
disorder in Fisher information is a measure of precision or localization, or I guess these different terms. But even in this minimax game theoretic formulation, it seems to be the case.
There's not much difference between this and minimax.
Now, what is it?
It is a minimax. It's a cross between Infomax, Minimax, and NDL. The only option, only reason, rationale I could give you is the one we talked about over a Coke, the Coke, where you minimize the information, you maximize the uncertainty to gain more information, so that the surprisal is there. I mean, that's why water would flow downwards. So we create the trough.
Yeah.
We empty the trough by creating,
Question.
because this is, I don't know if I'm right in saying this, but perhaps what you're saying is correct in a one-way street. But here it's a two-way street. It's me to him and him to me. It's the observer to the system and the system to the observer. That I have to give a thought. And David Otto's paper does give us a view of looking at the source of the game. But this has been used in two practical applications, just for your information. And money was made. I'll tell you where one of the practical applications which was used by MSR. IBM uses a privacy protection program written by Agarwal and Srikanth, whereby they talk about adding noise to IID data in a database and then trying to reconstruct the probability density functions. Now here we don't add noise to IID data. It can be arbitrary. It can be anything. The IIDs that is measured. We are not adding noise to the IID data which is being measured. Number one. Number two, you see the quality of the reconstructions. I mean, even for they use a triangular reconstruction and they use a simple one Gaussian reconstruction, and you still had wiggles. And in our particular case, sorry, it's bad manners to talk good about one's work, but one has to defend one's case. They could never reproduce this with their MDL type approach. So we can compress data into difference or lattice equations and send it across. The next part, which I don't have time here to show, but which if any of you are interested, I could send you a paper, is a time-dependent reconstruction. And that is really interesting, because the true crux both of Sungdao Lee's theories as well as this particular game phenomena comes out. But this too, in its form, has made. So this has been used as a database privacy preservation scheme, and it's also been used to as for quantum registrar. The time dependent is used in a more advanced privacy protection scheme, and also for more advanced quantum registers too. Any other questions? But Professor Fry, what you said may be true for one-way street. I don't know, I'll have to check that out. But this is the answer I could think of when we did it. But in a two-way street, where I want to make myself, it's like a prepared state in quantum mechanics. I want to prepare myself to receive as much information as possible, is by emptying myself so that I can be filled. Thank you.
Sometimes what I use to write down these